Hello my friends, and welcome to another Ionic video. In this one we're going to be looking at bonding, and specifically ionic bonding. We're going to also have some other videos on covalent bonding and metallic bonding, so check those out too. We're going to cover what bonds are, we'll look at how ionic bonds work, how to draw them, give you a chance to try some yourself, and then what ionic substances look like and how they end up having certain properties. The first area we need to work on in what bonding is what bonds are. And bonds are the things that cause atoms or ions to stick together. We know things like water are made up of hydrogen and oxygen, but the bond is the things that hold the actual atom together, the atoms together in this molecule. And they're held together by just one set of forces, and they're called electrostatic forces. If you think about what static forces are, they are an interaction between a positive and a negative charge. So if you're rubbing a balloon against your hair, for example, one of the balloon or your hair loses or gains charge, and so they are attracted to each other because one is positive and one is negative. The same is true for these atoms. And it's because of either the transfer or sharing of electrons. So they're either transferred or shared, though, to make the atom have a full outer shell, and that's what makes it stable. And we're going to focus in this session on ionic bonding, which is between a metal and a non-metal. An ionic bond is when a non-metal and a metal are reacting together. So this is metals from the left-hand side of the periodic table reacting with something from the right-hand side of the periodic table. Now, traditionally, this is with groups 1, 2, or 3 reacting with groups 5, 6, or 7. Because groups 1, 2, and 3 all have 1, 2, or 3 electrons in their outer shell. Remember, the group number tells us how many electrons there are in the outer shell of each atom. And in groups 5, 6, and 7, they all need either 1, 2, or 3 more electrons to get a full outer shell. So this type of bonding is literally where the metal will give an electron to the non-metal, and both of which then will have atoms, or now ions, that have a full outer shell. So as an example of that, lithium has 3 electrons in its outer shell. We know that because it's got a proton number of 3. So as an atom, it has 2 electrons in its first shell, and then in its outer shell it has 1 electron. If we then bond it with, let's say, fluorine, fluorine has 9 electrons in its atom structure. So fluorine has 1, 2 in its first shell. That leaves 7 in its second. 1, 2, 3, 4, 5, 6, 7. So what we can do here, or what happens, is when lithium reacts with fluorine very vigorously, it will donate lithium's electron to fluorine to give fluorine an extra electron, and both of which then would have a full outer shell. So lithium in effect loses this outer shell, and it reveals a full new outer shell, and fluorine has an outer shell too that is also full. So both of these now are much more stable than they were before. And that's the whole picture, that's the whole point of ionic bonds. Metals will lose electrons because they are on the left-hand side of the periodic table. They want to lose electrons to become have a full outer shell, so they become positive. We know that because electrons are negative, and so if they are losing negativity, they will become positive. And non-metals at the other end of the periodic table need to gain electrons to have a full outer shell. So if they gain negativity, they become more negative themselves. So how do we work out how to draw ionic bonds, and how is it structured? Well, I'm going to work through it step by step, and then I'm going to give you some examples to work through and try as well. If you forget how to do it or you get stuck, work back through this example, and hopefully should give you some more tips. So the first thing that we need to do is work out the electronic configuration of each atom we're trying to bond together. So let's say we're trying to bond sodium and chlorine, which makes table salt, standard ionic molecule. So we'll put sodium here, and we'll put chlorine here. Now sodium has 11 electrons, which means that it has 2 electrons in its first shell. It has a full outer shell, a full next shell, sorry, of 8 electrons. And it actually needs one more because we've got 10 electrons there drawn, and we need one more shell around the outside. 11. Chlorine on the other hand, has 17, so it's going to have 3 shells as well. So chlorine has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Once you've done that, you can realise how many electrons they need to lose or how many they need to gain. Now this is an optional step. You might be able to work out that from the periodic table, which you might be comfortable with doing. So using the group number to determine the outer shell of that atom and how many electrons it has. Sodium here, for example, has 271, whereas chlorine has 281, whereas chlorine has 287. So the sodium needs to lose this 1 electron, and chlorine needs to gain 1 more to have a full outer shell. That's what it's all about, getting a full outer shell. So the sodium here can donate 1 electron to this chlorine for them both to then be stable. So part 2 is working out how many electrons does it need to gain or lose. As I say, you can do that using the periodic table if you're confident with doing that. So the sodium needs to lose 1, and the chlorine needs to gain 1. Then you draw just what is left of the outer shell, just what is left of the ion. So sodium here has lost its outer shell, so actually we don't need to draw anything around sodium now. It's just got a full, the next shell that's revealed is a full shell. Chlorine has, however, gained an electron, so we draw its original 7 atoms, and then we draw the extra atom it's gained as a dot. So the crosses here are representing what was originally chlorines, and then the dot is representing what has been donated from the sodium. What we then also have to do is put them in square brackets, like this, and the chlorine 2, to show that that is a boxed off ion now, and we need to also give it its charge. So sodium has lost a negative electron, so therefore it's become positive. Chlorine has gained an electron, therefore it's become negative. And that is, if you were asked to draw an ionic bond for sodium chloride, that is exactly what you would draw. So just to work through the stages again, I would recommend at this point, if you're not confident, by first drawing out the electron configuration of the atom. That is as you would find it in the periodic table, so sodium and chlorine. Working out then how many electrons are in its outer shell, and therefore how many does it need to gain or lose. Then I would go on to draw what has happened afterwards. So here the sodium's electron is going to the chlorine, so it's revealing the next layer of electrons. In the actual ionic bond, we don't need to draw that revealed layer of electrons. We just need to draw the square brackets for the sodium and give it its charge, which is positive, and the chlorine we need to draw the outer shell as it is now, which is with its original electrons, as well as this gained electron from the sodium. We put it in square brackets and we give it its charge as well. Okay, so there are going to be some example questions now. Give these a try. Just remember that for this last question, so lithium chloride and sodium fluoride, you should be able to do okay with the same method as before. But lithium oxide, just to make a point here, lithium has 1 electron in its outer shell, so it needs to lose 1 electron, whereas oxygen needs to gain 2 electrons, which is why it has this formula of lithium oxide with Li2O, so that they actually end up having 2 lithium, each losing 1 electron, giving it to the 1 oxygen. So 2 lithiums are giving away 1 electron each, and the oxygen is then gaining those 2, so then they are stable and they'll be happy. For the first 2 here, they're fairly simple because they're both the atoms are either from group 1 or group 7. So lithium is in group 1, chlorine is in group 7. Lithium being in group 1 needs to lose 1 electron, and chlorine being in group 7 needs to gain 1 electron. So what they're going to do is the lithium is going to give 1 electron to the chlorine, and it's going to end up having a full outer shell in each ion now, and they're going to be happy and stable. So in the square brackets we'll have lithium. We don't need to draw any electrons here because their full next shell has been revealed. And in the chlorine, we draw its now complete outer shell, which will have 7 of its original electrons. and then the extra 1 from lithium, which we should draw in this case as a dot to represent that it's not come from chlorine. You could do the dots for chlorines at electrons, and you could do the cross for lithiums. It doesn't really matter as long as you have different symbols for each one. So chlorine has gained 1 electron, therefore it is now negative. We don't need to write 1 minus, but we could just put 1 minus there for the sake of it, because minus just assumes that it's minus 1. And lithium is plus. For sodium fluoride, sodium again is in group 1, fluorine is in group 7, so sodium needs to lose 1 electron, fluorine needs to gain 1 electron. So it's very similar setup, Na in square brackets with a plus because it's lost 1 electron, and then fluorine, we draw its outer shell of electrons here that it's now got. It had 7 originally in its outer shell because it's in group 7, and it's now gained an extra 1 electron. So it's now minus because it's gained 1 electron. Electrons are negative, it's now minus 1. Now for lithium oxide, it's slightly different. So lithium is in group 1, fine. Oxygen's in group 6. That means that oxygen needs to gain 2 electrons, whereas lithium only needs to lose 1. So we actually need in this case 2 lithium atoms, hence why the equation here has Li2O. We need 2 lithium atoms to give their electrons, their outer shell electron, to oxygen, so that oxygen then has a full outer shell. So we can do 2 square brackets here of lithium to show that, Li plus and Li plus, and then you draw your 1 oxygen with its outer shell, cross, 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 cross. There's its 6 original electrons it had in its outer shell because it's in group 6. And then 2 more that it's gained from each of these lithium. That goes in square brackets, and because it's gained 2 electrons, it's not just minus, it's 2 minus. Happy days. I hope you got that. If you didn't, go back and watch the tips on how to draw ionic bonds again, give them another try, and if you get it right, really good stuff. That's as complicated as they should get in the GCSE. For the next part, we're going to focus on what properties ionic substances have and how the bonding explains these properties. Well, firstly, they exist as what we call a giant structure, which is called a lattice. They don't really exist as small molecules as ionic substances. They tend to exist as large crystals when they're on their own, or they're not dissolved in things. And these are called lattices, and they're held together by strong electrostatic forces. Now, electrostatic force is just a force of attraction between a negative and a positive. These things will pull each other together a bit like magnets, really, and it will hold them together, and that's quite strong. That's what the actual bond is. It's not a physical connection, it's an electrostatic force that's connecting them. There isn't really any physical connection in chemistry, but yeah, that's a physics question, really. But these forces act in all directions in the lattice. So you've got here some positives, which are the sodiums. This is sodium chloride, and you've got some negatives in the chlorine, and they kind of hold each other together like a bunch of magnets in a space, and they end up working together to form quite uniform structures. Because of this strong electrostatic force, they have some properties, and these are quite important. So first up, they have a high melting point and a high boiling point. And that's because there is a strong force holding these together, linking these together and bonding them together. So we need to give lots of energy for a solid to be broken up into a liquid. What we're doing when we're turning a solid into a liquid is we're breaking or separating the intermolecular forces. And so we're putting energy in to break those apart. So intermolecular forces. Whether we're turning it from a solid into a liquid or a liquid into a gas, that's still very high, the amount of energy we need to put in. And you'd think because they're positive and negative that they might be able to conduct electricity, because electricity, you place electrodes at either end of a substance and you have a flow of charge. The negatives will get attracted towards the positive, and the positives will get attracted towards the negative, which is true, but only if these are melted or they're dissolved. So if they're added into a liquid or they are heated up to make them a liquid, then they can move. But when they're a solid, they cannot conduct electricity. Only when they are molten and these ions, which are these charged atoms, when these ions can flow freely, only then can they conduct electricity. But that's it for ionic substances and ionic bonds today. If you have any questions, queries, drop them in the comments section below, and do like and subscribe and check out the other bonding videos.